So this is our last topic. Let's do the screen. There we are. So we're talking about advanced statistical tools today. We're just scratching the surface on these. After doing today's lecture, you probably will not be able to jump right in and do principal component analysis, but you'll at least see what the goal is of principal component analysis. And then we will talk about correlation, positive and negative correlation, and whether it's statistically significant or not. So let's jump into that. So this multivariate statistics is the application of statistics to multiple variables. And some of these are not numerical, so you have to code them. Okay, so sometimes you have non-numerical things like color. Of course, now after PCHEM and the RGB lab, you know you can quantify color and get numbers associated with it. But sometimes it's just maybe the depth of color, lightly colored, strongly colored. I mean, how do you put that into a statistical program? We have to code those, like kind of like you do with strongly agree, strongly disagree. You put a +1, 2, 3, 4, 5, or -2, -1, 0, 1, 2, and you can code textual conclusions or opinions into numbers, and then you can use those as categories in a statistical package. In this particular example today, though, we're going to have numerical data, so that'll be nice. So here is our exploratory data analysis that we're going to do today. So the scenario is that there were 3 seizures of cocaine. And now this could be 3 separate seizures, or it could be, say, they open the trunk and they find a bunch of bags of cocaine. And they're in 3 groups. Either they're bagged together into 3 groups, or they have slightly different colors. Maybe some are in a blue Ziploc type bag and others in a white Ziploc bag. So they label them separately because there might be a significant difference between them, or there may not be. Okay, so that's the question. Are these 3 seizures from the same batch? Are they the same in their concentrations? Or are there any patterns within the groups? Could they be related in some way? Are they from the same source or same prep method, and so on? So they'll analyze these for different substances, and they found 3 substances in each bag, and we'll see what those are. Those substances are cocaine, procaine, and caffeine. So there's a lot, it's almost all of these drugs, there's lots of little variations in it. So there's cocaine, and then there's procaine and xylocaine, and even in like methamphetamine, there's the different R and S stereoisomers. And so there's lots of different types of these drugs. So here's a couple of types. There's cocaine, procaine, and caffeine detected in these. Now, one thing I'd like to point out is this skill of blocking data. Notice how the cases, or these little baggies, there were 10 analyzed in each little group. Notice how they're labeled. They're labeled, essentially baggie A, sample 1, bag A, sample 2, bag A, sample 3. And if you were to do statistics on this set of 4 columns, it wouldn't be very useful at all, because every row is a unique identified row. So the computer cannot tell that A1 and A2 are from the same batch A, unless you split those into separate columns. So if you just enter the data as it is, or take it as it is given to you on a spreadsheet, and it's A1, A2, A3, that's going to really confuse the computer because it's not blocked by A. You need a separate column that has just A's in it. So what we're building is a database, really. And so this is something you need to write down. In a database, every row is a unique record. Okay, so the record equals a row. And then each column is called a field. So the columns are fields. Let's see. Okay, and you hear that term all the time, different records in the database, okay? Now, each row really should have a unique identifier. And so in this case, we do have that case ID. That's a unique identifier for each row. Notice that none of those can have the same case ID. A1 is different than B1, A10 is different than B10, and so on. So that would be your unique identifier. For you guys, it's your student ID number. So that would define your row. And then in every one of your columns would be everything about you. Home address, telephone, grade in PCHEM 1. You know, everything that the university has on you is in a database, and each row, one row for each student, and each column is everything that they can search for related to you. So if something you add to a new class, it goes on your row as a new field. Okay. So what we want to do is take that case ID, which is the unique identifier. It has information in it, and we want to split that information out into new fields. So we want to create two new rows. So the case ID column is split into two new columns so that the data can be blocked by seizure A, B, and C. So we create a seizure column, and notice how there's lots of repeated information in there. Okay, so we have all of the A samples have A in that column, and all of the B samples have B in that column, so that the computer knows all of these are A, or all of these are B. So it can compare the average of the A group to the average of the B group and see if they're significantly different. It couldn't do that before we broke it apart. Now then we have a packet, like 1 through 10. Probably not any significant information there. Like, what is the average of packets number 2 or packets number 5, right? But there could be something there, but we won't analyze that because it's just 10 packets from A, 10 packets from B, and so on. But you could. Maybe there would be something significant in that column, but in this case, there's not. So does everybody understand really what blocking is? It's another way to say grouping. Okay. And then naturally, we could look through our university records and we could say block all of the students who took a particular course and see what that course average is. And then we have dates in there. So we could say, what about this course in 2012? What about this course in 2022? And see how those groups, their averages, means, standard deviations, all of the statistics associated with those things. So this idea of database and blocking is universal. It doesn't have to do with forensic chemistry. It's just how we deal with data. But it's an important concept, this blocking idea. So I'm using a lot of mini-tab graphics here. So this is a 3D scatter plot, and this is how you do that. You go up to the graph, and 3D scatter plot is an option under the graph. You could pick a simple scatter plot that just scatter plots all the data, or you could do it with groups. And when you pick with groups and hit OK, you get this dialog box where you pick the Z, Y, and X variables. You have total freedom of which you plot on each axis. And then this down here is the the groups that we have. So we have it grouped by seizure. Okay. And so we see up here these different groups are now different colors. So we have the A, B, and C groups plotted on here. And just looking at this, what do you see? Go ahead.
B and C are...
Yeah, B and C are all mixed together, and A is off by itself. So immediately we have a conclusion that A is unique when compared to B and C, that there's a difference between those two groups. You can learn something too, because this is a quantitative graph. Which of these groups, A, B, and C, has got the most cocaine in it? A is high in cocaine, and B and C are high in procaine, and everything's kind of high in caffeine. They're using caffeine to kind of mask the absence of cocaine. So you get the expensive stuff, the cocaine in, and you want to make a bunch of cheap street samples. So you're going to take a little cocaine and you're going to throw in some no-dos. That's really cheap. Throw in some caffeine, maybe some procaine to mask the weaker cocaine. So you're trying to stretch your supply of the good stuff. Okay. So it looks like A is different from B and C. That's one of our conclusions. And that there is a correlation between cocaine and procaine. So when cocaine is high, procaine is low. Let's see. Do we see that? We'll see if that maybe more clearly later. but still there's definitely a difference in cocaine in sample A versus B and C. Okay, so here's a box plot of the same data. So if you go to graph box plot, you get this option. You can do, if you have just one Y, so just one variable, you can do a simple or with groups. If you have multiple Ys, you do simple with groups. And so we have multiple Ys because we have cocaine concentration, procaine concentration, and caffeine concentration. So we have multiple Y variables. And so we're going to pick multiple, and we want to group it by A, B, and C. So we have here this, we have here the multiple Y's with groups, hit OK, and then we get this dialog box. So we put all three Y variables in here, meaning all three of our numerical variables, cocaine, procaine, and caffeine. And then we group that by seizure. And so the seizure groups are A, B, and C that are down here. And then below that, you have the three Y variables. And then you have box plots. And remember, the box plots tell us the middle of the box is the mean. The line in the box is the median, okay? And then the whiskers give us the range. And so that tells you the top point and the bottom point. And the nice thing about box plots is they do outlier tests for you, and we don't see any outliers. Okay. So what are your conclusions here? So this is group A. We see the cocaine is really high. And here's the group B and C. Cocaine is low here and cocaine is low there. So we definitely see a difference in cocaine amount. The procaine amounts are pretty similar, and the caffeine amounts are pretty similar. So it's really the difference between A and B and C are the cocaine amounts. So sure enough, A looks different than B and C. Now, how can we tell, like when we want to make that claim that something is different in a box plot, you really need to look at the overlap of the boxes. So let's look at just the caffeine samples. See how those boxes, if we look at them from the left, they overlap. So if we look at these boxes from the left, we can't tell the difference between them because they're overlapping each other. So they're all essentially from the same population in terms of caffeine. But if we look at the cocaine from the left, we see this group here and we see this group here. So and they don't even overlap. So the sample A, that box and the whiskers are above the boxes and whiskers of the other two. So in a box plot, if you want to say that they're significantly different, the boxes should not overlap at all. If the boxes overlap, then there may not be a statistically significant difference. And that may be the case with procaine. You see this here, they do hit each other, at least the ranges do. Like this one it looks significantly different, but it might hit this other, it definitely hits this lower value on the range. So we'd have to go look at the numbers to see, like the actual, t-test on the equal means. So that's a box plot grouped by the seizure value. Now this one is a really confusing plot, but it's okay. It's called a matrix plot of correlations. So if you go to graph and click matrix plot, you get all kinds of these options here. I did, again, each Y versus each X. So I'll fill out the full the full matrix. Notice some of these different plots. You can have just the simple plot or the simple one with groups, or you can smooth the data, like draw lines on it. If I'd chosen this one, it wouldn't show the diagonals. Okay, notice the diagonals are missing here. But if I show the diagonals, we can we can see what we get out of those. So this is every variable plotted by every other variable. So we have 3 variables, and so we're going to have 9 panels. Okay, even the ones that are plotted by themselves. So we have here cocaine concentration plotted by cocaine concentration. Okay, so that's why it's a straight line. But at least we see that there's a gap here, and all of the A values are high in cocaine, and then the B and C are mixed with each other. So even the one where you're plotting the variable by itself or against itself, you get this straight line. You can still make a judgment if it's something like this, where you've got a dramatic difference in cocaine. Here there's some overlap when we plot procaine by procaine, and here we've got some overlap here. The cocaine or A samples are all mixed in with B and C in terms of caffeine. Now let's look at the other correlations. Let's plot when cocaine is plotted versus the procaine concentration. It looks like over here when the cocaine is high, there's very little procaine samples, and when procaine is high, there's very little cocaine. So we have this negative correlation between the two. And these two panels are essentially the same. It's just that the Y and the X values are swapped. Okay, so this is procaine on the Y-axis and cocaine on the X-axis, and this is vice versa. So this is now cocaine on the Y-axis and procaine on the X-axis. And then here's caffeine plotted versus cocaine, and then here's caffeine plotted versus procaine. So there's really not many other conclusions you can get from this, but this is every pairwise combination. So if you had 5 or 6 data points, you'd have a 6 by 6 matrix, and it would be every pairwise set of variables plotted against each other. So let's look at the correlation matrix. If we wanted to see some numbers associated with these correlations. So these are the visual correlations. So let's take now this calculate y equals mx plus b and see if that trend is statistically significant. So let's get a p-value for this. And so that's what this correlation matrix is. So we go to stat, it's not a graph, it's just a statistical tool. Basic statistics, correlation. So those are the menu items. You start at the stat menu, then you go to basic statistics, and then you select correlation. And the 3 dots will tell you it's going to give you a dialog box. And then it'll display the p-values. And so the null hypothesis is there's no correlation. And the p-value obviously is the probability that the null hypothesis is true. And the results are this Pearson correlation coefficient. So this is a different R than what we got from our regression analysis. This is actually telling us kind of like the coefficient M. It's kind of like the slope value. And so these are the dialog box that you get. You grab all 3 variables, and it'll do all 3 combinations of cocaine, procaine, and caffeine. And so this is our table that we get here. And this would be in the session log. So if you're doing your statistics in Minitab, all of the things that you do show up in the session log. And when you do stat, basic statistics, correlation, fill out your things, hit OK, you don't see a graph pop up or anything like that. I think maybe the session log pops to the front, but if it doesn't, you have to go see what the results were. You may see that nothing happened. You're like, oh, what happened? Well, you go to the session log and you'll see the output. And this is what you would get. So the cocaine-procaine correlation is this negative 520. That's the correlation constant or coefficient. And so it's saying it's negatively correlated. So what that means is if cocaine goes up, procaine goes down. And it's roughly quantitative. So if cocaine goes up by 1, procaine goes down by 1/2. So it's a pretty strong correlation. And then the p-value is the probability that this correlation is 0. Okay, and it's 0.003. So it's a pretty small probability that this correlation is 0. So it's saying it's a strong negative correlation between cocaine and procaine. What about caffeine? Well, caffeine has a positive correlation with cocaine down here. So it's saying that when cocaine goes up, say by 1, then caffeine goes up by 1/2. So it's a positive correlation. They track together. And then what's the probability that that's 0 or no correlation? 0.005. Now, the caffeine-procaine is showing a negative correlation, but it's really weak. It's 0.04. So it's saying if procaine goes up, caffeine goes down by 0.04 amounts. And so that's not very much at all. And this is the probability that it's 0. So 83% chance that this is no correlation at all. So this one is not statistically significant. Because you look at that p-value, it's 0.83. And our alpha is 0.05 for 95% confidence. So they need to be less than 0.05 for us to say they're statistically significant. We can see this on the box plot now if we look at that. we see if going from here to here, cocaine went down, right? And when cocaine went down, procaine went up. You see, this was procaine before, and here it is after. See, it's going up. So we could have seen that from the box plot. If we'd looked at it carefully enough, we could have seen, oh, look, cocaine went down and both the procaines went up in B and C. And they went up about half the amount. So that's where the 0.5 comes from. So the negative sign just means they're in opposite direction. So if cocaine drops, the procaine goes up. If cocaine goes up, the procaine drops. Okay. What we really couldn't see from the box plot was this correlation in the same direction of the caffeine. So it's saying as cocaine went down, okay, caffeine significantly dropped as well by 0.5. Okay, and it's 0.5 of the caffeine value, so it only went down a little bit relative because it was already a low number. So cocaine dropped, say, 1 unit, and caffeine went down a half a unit of what it already had. So it's a really small amount. So let's look at the top hat now. Let's go. So this is the one tool, this correlation, that I think you would come across more frequently. So that's why I'm testing you on it, and it's going to be on Tuesday's test. Okay. What happened here? Oh, I see. Yeah, let's present. Unassign and present. Okay. So looking at this figure, which pairs are significantly correlated? Select all that apply. If you can, I'm not sure if you can. So if you can only select one, pick your favorite. Okay. And let me know, can you select more than one? Do you have checkboxes or only just one radio button? Just one, okay. That's too disappointing. Okay, hurry up. 15 seconds. Okay, got in right under the wire. Okay. So let's look at the answers now. So everybody liked the procaine-cocaine correlation and caffeine and cocaine. I spelled that kind of funny, didn't I? Okay, so these are the correct answers. They were statistically significant. So for this one, significantly correlated statistically means we're looking at p-values, right? Okay. All right, so of the statistically significant correlations, which pair is negatively correlated? Okay. Now we have the caffeine and procaine here that is negatively correlated, but it's not statistically significant. So we would not really talk about that correlation coefficient because it's not reliable statistically. So we just say there's no correlation there. We don't really know that that sign is negative or positive because our null hypothesis is that it's zero. So zero is no correlation, no positive, no negative correlation, and there's an 84% chance that it's zero. So we'll just just not even talk about procaine and caffeine, or we'll say that it's not correlated statistically. So this is, of these two, the top one is negatively correlated. So for correlation coefficient, we're looking at two things. The sign is important. So it means when one goes up, the other goes down if it's negatively correlated. Now that's, listen to carefully, I'm not saying it's inversely correlated, it's negatively correlated. So when we say proportional to or inversely proportional, we're talking about whether it's, like they both go up, but inversely proportional, that's more of a mathematical relationship that we're talking about there. It's 1 over x dependency, whereas this is just talking about positive and negative correlation. So that's, of course, the top one is the correct one. Procaine and cocaine are statistically significant and they're negatively correlated. All right, so let's go back and assign these. Very good. Okay. And so now let's look at some other tools. This one is really useful when you have even more than 3 data points. So cluster analysis. And so let's, this is also called a dendogram. So that's a new word for you perhaps. Okay. So any objects that branch are called dendrites. So you can think of like a tree. You've got a trunk and it splits into boughs, which splits into branches, which splits into twigs. And all those branchings, that's called the dendritic effect, or dendrites. Okay. And this is a dendrite or dendrogram where you're taking the data and splitting it apart. But actually it's built from the bottom up. So let's take our data here. And this is just in 2 dimensions, x and y. What we want to do is we want to take the data and cluster it. So we calculate the distance matrix. So we take the distance between point 1 and 2, point 1 and 3, 1 and 4, 1 and 5, and then 2 and 3, 2, 4, 2, 5, and then 3, 4, and 5, and then 4 and 5. So we take all of the pairwise distances and we sort them. And the one that has the closest distance, or the smallest distance between the 2 particles, then we join those together. And so in this case, 2 and 3 are the closest. You see what we've done? We've drawn now a circle around 2 and 3. And over here, that would be this represented by this right here. So this linkage distance, we calculate that distance. This is the smallest distance here, and it's between 2 and 3, and so we connect 2 and 3 with a horizontal line. Make sense? Pretty easy, okay? Now we take the center of that pairing and recalculate all the distances. So we would take the center of 2 and 3 and calculate the distance to 1, the distance to 4, the distance to 5, and sort them and see what's the next closest distance, right? And then we also do, 1 and that, 1 and 4, 1 and 5. So we do those distances and we do 4 to 5. But the next closest one is the distance between 1 and that cluster. So this distance right here is the next smallest distance. And so that's going to be this one here. So we draw a line between this joined cluster and data point number 1. That's the next distance. So when we combine that into a cluster, it has a center point, which is the average of all 3 of those points. And then we calculate that distance to 4, that distance to 5, and then the distance between 4 and 5. And we see that the distance between 4 and 5 is the next smallest distance. It shows up right here. And so we draw a connecting line between 4 and 5. And then we combine those. And so now we just have 2 groups. We have a group that contains 1, 2, and 3. And we have a group that contains 4 and 5. And notice how this is a way to see if we have groups in the data. When you get to this point, you realize I've got 2 groups that can explain this large, complex, 2-dimensional data. And that's what you're really trying to figure out. How can we group the data? And the nice thing about this is you could have this in 3 dimensions, 4 dimensions, 5 dimensions. Think about how would you visualize a 5-dimensional data set? There's no way to do it, but you could with this. You could see that this particular group has these 3 dimensions that are all similar, and this one has those 4 dimensions that are similar. Maybe a third group has only 2 of these dimensions that are similar, and you would be able to pull out associations from a really complex data set. And so then we combine those last 2 and it comes into one group. So this is, whenever you see, the last one is really meaningless, right? It's the distance between the 2 groups. But I guess what's maybe not meaningless is this distance here. So that's how different the 2 groups are. Where can I write this? Right, because if they were like this, 4 and 5, that distance would be small, and this line would be right here. You see, and the 2 groups wouldn't be that different. But if there's a really tall thing, and then you have that line across, there's a big difference between the 2 groups, and it should be really easy to separate those 2 groups. And then if you, like, some of these variables could be, could even be a coded color, right? So you could, if you had assigned numbers for colors, then you could have color on here, and you would detect whether these groups had a different color too, because color would be associated with one of those variables. So, okay. So that's a dendogram. I also like to ask questions about it because it is such a useful tool. So here's the dendogram for our cocaine, procaine, and caffeine. So we have 3 variables, which again, we could plot them on an XY scatter plot, XYZ scatter plot, but this is everything plotted in 2 dimensions. So let's see what's going on. What do we know from this dendogram? So the first question is, what are the most similar samples? So right there, B6 and C8 are the closest together in terms of all 3 of their concentrations. So they have the most similar cocaine, procaine, and caffeine concentrations are B6 and C8. What about the next one? There's kind of a big gap between those and the next one, B8 and C6. Okay, that's kind of weird, B8 and C6 and C8 and B6, but anyway. And then B2 and B7 are in the next group. And then we join in C2 to that group. So we're just working our way up from the bottom, seeing our different groups. And then the next one is this B9 and C4. What are you learning from this so far? Is there anything you can draw? What?
The taller they are, I guess, higher the numbers.
Yeah, so the taller they are, the further apart they are. Okay. So see, B6 and C8 are really close to each other. Those data points are almost on top of each other because the distance between those 2 data points in 3 dimensions is almost nothing. And then we're joining in the next ones. What do we know from the letters and numbers I'm calling out?
It's only B and C that are showing.
Yeah. All of their closest data points are all B's and C's, and it's a mixture. Some B's and C's and some B's with each other. So the B's and C's are all very close to each other. No A's so far. And then finally we get our first group over to the left. Those are A's, A5 and A9. And then 7, this like we go through all of these and notice all of this group is all of the B's. There are no A's down here at all. So this whole group here is the B and C group. And then we have all of these over here. Notice all 10 A's are here. And then we have that oddball B1. In fact, if you were to compare B1 to the B and C group, it might be an outlier, because look at the distance between the others and B1. So this is the average. This would be the distance, or the average of all of these in terms of their concentration, the distance to the average of this B1 value. Okay. And so when you look at this, you see all of these are intermixed. It tells you that there's two groups in the data. Okay. Two groups and maybe an outlier. Okay. So we could have, of course, we could have gotten that from the XY scatter plot or some of these other tools. I'm just showing you a survey of all the different kinds of tools that you can use. But this sometimes the Dendogram can pull things out of the data that are hard to get from some of the more quantitative charts. Then we enter into principal component analysis. Okay, and this would be helpful if we couldn't make a scatter plot. So we had this 3D scatter plot, but what if you had a fourth dimension? How would you plot that? You know, that is going to be really difficult to do. You'd have to pick three important variables and then maybe color code it for a fourth. And so when the number of data fields or attributes is greater than 3, then we do data reduction. And so this reduces the data space. In our case, our space is 3-dimensional. We have cocaine, procaine, and caffeine for our data space. And so this produces linear combinations of those. So for example, if caffeine is pretty much the same in all of them, there's really no need to plot the caffeine variable. We can just fold that caffeine variable into the cocaine and procaine variables and plot it with two new factors and get it down to a 2-dimensional plot. So that's what principal component analysis is. Think about that word. It's looking for the principal components that can describe the data. And it's really looking for two. So it's going to take combinations of all the others and produce two new axes that are not pure axes in relationship to any of our data. So there's not going to be an axis that's cocaine and an axis that's procaine. It's going to be an axis that is a ymx plus b, y equals mx plus b of our variables, or really be mx plus zy plus tz plus b is one axis, and then some other model for the y-axis. And so you could go up here to stat, multivariate factor analysis. And so then you put in your variables and extract two factors. So it's going to produce two axes, and it's going to use principal components for those. And then there's different types of rotations. It can rotate these to more equally mix the scatter that's captured. And so what we're looking for is the percent variation that's covered by the factors. It's kind of like an R-squared value. Okay. So here's from the session log, this is what we get, our factor analysis for these three. Okay. And so we're getting 90% of the variability is modeled by these two factors. And so here, factor 1 is covering 58% of the variability, and factor 2 is 32% of the variability. So that's the unrotated PCA, principal component analysis. If we rotate that, it just rotates the models, and you get different coefficients, and then you kind of get a more even split of the variability. So factor 1 now is covering 46% of the variability, and factor 2 is covering 44% of the variability. Now, what do I mean by factors? Look, here's the linear equation right here. And here's our variables. So our factor 1, our x-axis, if we were to plot these, would be, I'll say x is equal to 0.92 times cocaine. I'll put an O here for cocaine, minus 0.68 times procaine, plus 0.66 times caffeine, Ca. So you see how now we have an axis, but that axis is a model or a factor of our data. It's a linear relationship of our data, and then the y-axis is really not using the cocaine at all, is equal to essentially negative 0.002 times cocaine plus 0.68 times procaine plus 0.71 times caffeine. So the major factor in the x-axis is the cocaine value, plus a little bit of procaine and some caffeine, and then notice how the y-axis is mostly just procaine and caffeine, almost no cocaine. And so what this is trying to do is to get our data to split out as far as possible. And so this is what we end up with. This is our score plot. It looks very much like our correlation plot of caffeine versus procaine, but this has got essentially the best possible separation between these two factors. Okay. So if we had 4 or 5 variables, our X and Y models would be 4 or 5 terms in those, and it would have found the best combination of those terms to get the biggest separation in our data. And so that's it. We're going to go questions now on homeworks and everything like that. So did you have questions on? Yeah, go ahead. I'll go back.
So for one, you said that those are most similar.
Yes.
But would the ones that are most similar to one be the ones closest? Like the next one over like 5? Like how do you know, how do they correlate after?
I'm not following the question.
Which data points would be most similar to one?
Okay, so then this grouping here doesn't get pulled in until up here. Okay, and so we have some others. The next one, I drew this one at 2 because this is the next closest, like the distance. So I'm going up the distance scale. This little group was the next closest. So if we scatter plot this data, B6 and C8 were closest together. So we draw a little circle around them. And then everything else is pretty far away from that pair. We're looking at the data cloud and we see, okay, B8 and C6 over here are closer together, the next closest together. And so we connect them with a circle. And then 3 and then 4 we tie in. And then we get over to 5, and now this B9 and C4 are close together, and they're pretty close to B6 and C8. They get joined pretty soon afterwards. So we join those together. Now, how they plot this x-axis, like in the dendrogram, how they decide, what to put, why was this pair plotted here and not like first? Is that what you're asking?
So you're saying by the height, you said 2 is like the next.
Yeah, so this is the next group. So let me go back to this previous slide. So here we had our data plotted, and we analyzed the distance between all of the pairwise points. So we went 1 to 2, 1 to 3, 1 to 4, 1 to 5. And then we went to point number 2, and we've already calculated 1 to 2. So then we start with 3. So we go 2, 3, 2, 4, 2, 5. And then we go to 3.
In this case, 2 and 3 are most similar.
Yeah.
And 1 is the one that's similar to both of them. Is
Yes.
that because of the height of the bar, or is that because it's right next to?
Because it's right next. So we're really we don't have a Z in this particular data set. So we're just doing X's and Y's. And so then when we circle that, we draw a new data point in the middle of that little cluster. And 1 is the closest to that point. So then we draw a circle around all 3. And we put another point in the center of that cluster. And now we're calculating the distance to the center of that cluster. And notice how the 2 and 3 were joined together. And then the center of that cluster is joined with 1. And this is the distance between 1 and 2, 3. So 1, 2, 2, 3 distance is that little bitty stem right there. Yeah, and so that's represented by this line right there. So that is this tiny little distance right there. And then the 2, 3 distance here is this, let me go around here, is this distance right here. So we calculate all the distances. The 2, 3 distance is the smallest. And so we create this matrix like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So you could do this in Excel. The 1, 1 distance is irrelevant, right? But you have the 1, 2 distance. And so you have a number there. The 1, 3, the 1, 4, the 1, 5. And then you go to 2 and calculate the 2, 3 distance. 4, 5. And then you go down to 3 and calculate the 4, 5 distance. And then you go to 4 and calculate the 4, 5 distance. So these are all the distances that you have in this top plot. And you look at all of them and you say, oh, look here, the 2, 3 distance. So this one here, 2 to 3, that's the smallest number in the whole triangle. And then on the y-axis, you pick that number and you draw a line connecting data points 2 and 3. And so then now that's got a cluster, and you have you take data points 2 and 3 out of this matrix and you put in the location of the cluster, the first cluster, and recalculate the distance matrix. Yeah. So this is very easy for a computer to do with a for next loop, right? I've got a list of data points, and I go through for every data point in this list, calculate the data point for n plus 1 and all the other n's, and you just loop through this, and so it's very fast, and it produces. And then you're looking for the minimum. You say, is the last data point less than my minimum? If yes, then replace the minimum. If not, go on, and it'll find the minimum, and then you can draw this graph. So whenever you see a large, I guess this is the key, this last thing, you can tell very easily what the closest data points are. And then when you have this large top on a dendrogram, you have really distinct groups. So let's just go, because it's a good question, it's a good thing to look at. Let's go to the internet and look up dendograms online. Okay. Let's see. And so here we have lots. Okay, so you can go on here and see them. Yeah. Okay, and so look here. Let's look at this one. Let me open this in a new tab. Open image in new tab. Okay, and then let's see if I'm getting that. Yeah, I'm getting it. Okay. Okay, so I don't know what they're actually plotting here, but we've got lots of cities. I guess it may be distance between the cities. So here, you've got Rio, Buenos Aires, Cape Town, and comparing that to Caracas, Chicago, Montreal, New York, Washington, D.C., Honolulu, Mexico City, Los Angeles, California. And so you can see that they're grouped. And then what you see is this large piece here is saying there's a large distance between this group and this group. And since that's such a large distance, I know these two groups are distinct from each other. And then let me back up. Okay. And then I've got a really large distance here that caps these two groups. So I know that these two groups are very distinct. And since I'm looking at this big, huge rectangle on top here and this big, huge rectangle on top here, that tells me, since both of these are large, that I have 4 groups. If one of these is really small, Like, see, this one's kind of small. All right. If this one were really small too, I would just say these are all one group. And I would have this one group and then this one and this one. And I would say there's 3 groups in my data. Okay. I mean, you're always going to get to the top where you have everything combined into one. So you're going to have one, but what we're looking at is this distance here. This distance right there compared to this distance right there. If those are pretty even and it's long, you have 2 huge separations in those groups. Okay. It's a judgment call because there's not really a number associated with it, but the number is that distance. And so if that's a large distance between the 2 groups, then you know they're well separated, right? And that's what we see here. We see this large distance between group 4 and 5 and group 1, 2, 3. And so we know they're well separated, so they're far apart. And we look at our original data set. Since it's 2 dimensional, we can see it. We can see there's a large distance between this group here and that cluster there. Okay. So when we look at our data, we see that there's a large distance here. This distance here is pretty large. And this is, this distance is comparable. It's about half the size. But we've got a couple of oddballs here. So this one's kind of an oddball. So we're looking at 2 groups and a couple of oddballs. Okay, yes.
So this kind of pertains to this, but would result number 1 be the one that's already labeled 1 because it's the smallest and the smallest height on there? Or would it be the one that's actually like A1 as result number 1?
What do you mean by result number 1?
Well, it's pretty minimalist kind of, but I was just wondering because it said which analysis result is most similar to result number 1, so I'm kind of just wondering what the order.
Okay, so where is that? Which number is that? Let me just.
Yeah, it should be number 2.
On the last homework?
Yeah.
Okay. Okay, so let's look at that. Yeah, so this is for the camera here. We're looking at the homework. All right, so this one here, we're looking at these questions. Okay. So yeah, we have a dendogram there. Can you figure out which analysis results are the most similar? You can see that 2 and 10 are joined first, right? So those are most similar, okay? Then we look at that, which analysis result is most similar to result number 1. So we have our results listed there on the x-axis. And so it's just the first one that joins with it. So if I've got result number 1, the next closest result is number 4. So you just read the chart. If whatever's paired to number 1 first would be 4. Now, if it was like number 9, it'd be a little more complicated question because 9 is similar to the cluster of 5 and 8. So it's pretty close to both 5 and 8.
Well, would you just say that it was both? Is that one?
Yeah, you would say that it's kind of probably equidistant roughly from 5 and 8. That 5 and 8 are similar to each other, and then it's close to both of those. Does that make sense? Yeah, okay, good. And then the last one, number 10, which result's the most unique? Number 3, you see it's got its own little line going up, and it doesn't join with anything else until way at the top. Okay. Yeah. And so how many groups do we have in this data? It's going to be, you want it to be a small number, right? 1, 2, or 3, maybe 4. It'd be hard to establish 4 or 5 groups unless you had a lot of data. And so we're looking at these large vertical lines, okay? And so this is definitely a group over here because it doesn't join in until way late, okay? And then all of these join in. So we would have, I would say, at least 2 groups. Maybe this 1 and 4 are their own group. So I would go with 3. Notice I didn't ask that question because it's kind of a judgment call. So I would say 3, probably 3. Because 1 and 4 seem to form their own group. They're the last ones to get pulled in. And so I would say definitely one group is 3, 6, and 7. The other group is 2, 10, 5, 8, and 9. And then 1 and 4 seem to be their own thing.
Could 3 not be considered its own group?
Yeah, it's really by itself out there. Yeah, so it might, if it's a single data point though, you might call it an outlier versus a group. So it's not clustered with anything. So it's a unique point, which would make you want to investigate it. What's weird about 3? And then you go test to see if it's an outlier in any of its variables. Yeah. So that's good. Good questions on the homework. Naturally fed into those. So we've got 15 minutes. So let's go ahead and ask some questions. I've got all of the homework sets printed out here, so we can. Yes.
I had a question on the last homework. It was the end calculation of the slope.
Where's that?
It's question 1 on homework 4.
Okay. Back up. Question 1 on homework 4, quiz 4. Okay. Okay, very good. And so you would do those, sums of squares and all of that stuff if you wanted to.
I guess every time I tried to calculate it, I wasn't getting the same answer from Excel.
Oh, interesting. Okay.
Using that formula.
Yeah, I don't know. How different was it? Okay, let me look to see what we can find on
Like I got 17 million.
that. Yeah. Yeah.
I calculated it out like 3 or 4 times, and I just wasn't getting anything even.
Yeah, let me see if I can find that in the Excel file.
Because, I didn't know, we're going to have to hand calculate it for the exam.
Right. If you do the sums of squares and so on, then it takes a while. Let's see. So that's this one, 21. No, that's not it. Here we go, 2103. Away from 4. Yeah, excellent. Okay. So I'm getting, here's the sums of squares. Here's all of the numbers that you see. I'm going to put this on the video for you, okay? So let's turn on Excel. All right, so here's your sums of squares to check your work. So sums of x's, because x's are all pretty small numbers, 0.2 up to 100. It's a small sum xx. Here's the sum yy, which is huge because of our, thousands of numbers there. Then here's the x's and y's times each other. You add those together and, this is the average x value and average y value. So you take all 4 of the x values and average them. Did you do that? And then the y, this is the average signal from the y. We could do those ratios and get our r squared. And then here's the slope that I get. This is that sum of x y divided by sum of xx.
Okay.
Yeah. So that's what I'm getting is 622, and that's where I put the answer in. So there's got to be something in your, maybe in your parentheses or something with the sums. I don't know.
I think it's with the XY, because I have the same XX answer.
Okay.
So it's definitely something with an XY.
Okay, very good. Yeah, that's great. Yeah. All right, fantastic. Okay, next question. And it is really tedious to do that by hand, and it takes a long time. So, just from my perspective, I want to make sure everybody finishes the exam, right? And sum of squares, you're probably going to do in Excel, to be honest, right? But I wanted you to do one by hand here just to review. So the hand calculations that I want to see you demonstrate on the exam, of all of the things we've done by hand, what do you think my priority is in this class? Uncertainty, absolutely. Yeah, so focus on the uncertainty calculations for the written parts, because that's the skill that I think is less tested, and you can't do that one in Excel if you don't know how to do it by hand. Whereas you could do the sum of squares in Excel just by selecting ANOVA, So I want to make sure that, even, the propagation of uncertainty, if you don't know how to do that by hand, Excel is not going to help you. Yes?
For quiz 2 number 4, why is the answer 0.0 and not 0.02?
Quiz 2? Yeah, okay. Let's look at that. Number 4? Yeah, so it's because of the powers of 10. So let me pull up a blank PowerPoint. Let's see. Okay. Well, no, undo. I can't believe that's still in my clipboard. Okay. All right, here we go. Oops. Okay, so this was it's really difficult to do subtraction in scientific notation. So you got to get them all in the same power of 10. Okay, so if you have that 2.2 times 10 to the minus 2, and you're subtracting 2, oh, this is 2.0 here, 2.2, no, 2.0 times 10 to the minus 6. This is your problem here. So if you convert those over to decimal places, 0.0220, and you're subtracting then times 10 to the minus 6, so 1, 2, 3, 4, 5, 2, 0. So that's 2.0 times 10 to the minus 6. This is how I do it. I draw a dashed line here, so that I can put some more zeros in here to do my subtraction. 0, 0, 0. So I borrow all the way from that too. So I have 10 over here. Okay, well, I don't need to do anything because there's a 0. So I've got 10 right here. So 10 minus 2 is 8. Okay, but I borrow from a 0, so that was 10. Now it's 9. Okay, 9, 9, and then 1, and then 2, and 0. Okay, but my little dash line tells me where to round. Because whenever we're doing subtraction and addition, we, in decimal places, we keep track of the decimal places, not of the significant figures. And so when I round this, I end up with 0.0220. So it's as if nothing happened. Yeah, and that's because if I'm uncertain in this digit right here, I have no idea if I've subtracted this. So I can't detect it. So that rounding rules tell us where our certainty is, and it keeps us from all of a sudden producing something that's misleading. If my measurement truly was limited here in this decimal place, and I do a subtraction, and then I report this many significant figures, let's say this is a mass, right, in grams. So here, that's a 4-place balance. Right? I've got a 4-place balance. That's not a problem. But then I subtract some tiny little mass amount for whatever reason. And now I'm telling whoever I'm reporting this to that I've got a 7-place balance. So I'm misleading. I can't tell them that I know the mass out to 7 digits because I only have a 4-place balance. So we would say, yeah, I couldn't even detect that loss of a hydrogen or whatever it is, that tiny little thing. Yes?
I'm assuming we're not going to be able to use a calculator for our exam.
Oh, you can.
Oh, okay.
You can use a calculator for sure, yeah. Yay. Now, no note cards, because I found this class is much more sort of text-based, and people were just putting so much on their note card text-wise that they really didn't have to study. Okay, y'all think, hey, that's great, but that just means you don't learn anything. Okay, I'd like you to learn something. And so I'll give you an equation sheet, so you don't have to worry about not having equations. The propagation of uncertainties, we get into weird concentrations or something like that. You'll have equations, you'll have a periodic table and an equation sheet. Okay, so if you need an equation on the exam, it'll be on the equation sheet. And so you just need to learn the material and learn how to use those equations. So I really want you to study hard for these. Yeah, so that's the way we do it.
On number 20 on the last one that we were going over, I was just wondering if I look it out, what the answer to it was. I don't know if I look it out correctly.
Which
Homework 4.
Homework 4, okay.
Number 20.
Number 20.
It was one of the ones we were about the uncertainty.
Oh, yeah. Yeah, number 20. Yeah. That one we got 2 minutes, so I don't think I can.
Well, I mean, I worked it out.
Oh, you did?
Yeah.
Okay.
I don't know if I got it right.
It's 4.4
Okay.
milligrams per liter. Okay, very good. I didn't realize. I thought you wanted me to work it out. But no, that's the one where you do the x equals y minus b over m, and you do the numerator and uncertainty in the numerator. So good. In the back, yes? And after the due date, then the answers become visible. But did everybody know that? So after the due date, go back and look at the test, and you can see the answers. I make it turn on after the due date, so then you can go back and study from all of those. Okay. All right, y'all have a great day. Good luck on Tuesday. We'll have a fantastic day. Yes. Today at 10, I think. Yeah, today at 10. I have office hour on Thursday. You're like, but if you need an appointment, send me an email. Yeah, like to this afternoon or Friday. Yeah. All right. Yeah, just shoot me an email and we'll set something up.